video presentation, which provides a broad understanding of E2E's patent-pending EGRRS process. After the video, I'll provide a brief introduction to E2E Energy Solutions, specifically what inspired its creation and the potential opportunity it creates for the oil and gas industry. Dr. Sahar Gennady will then review the results of the simulations performed on the EGRRS process, followed by Jim Roycroft to discuss the financial potential of the process. We'll now start the video of the enhanced geothermal reservoir recovery system.
Do you hear the voice?
Yes.
Good.
I don't know.
Is there sound?
We
The
cannot
sound
hear the
of
video.
You don't hear the sound of video?
I'm not hearing the video, the words. No, the words are not playing.
How can
Can you just click on your video and just play it, Sahar, somewhere else? Or
Yeah.
let's just do that and then we'll come back to the presentation, because that's the most important part.
Okay.
you just open it in another window, maybe share a different window?
Yeah, I need to find it in. Do we have it in here? Presentation. Oh, is that the same?
That's the one, yeah.
Doesn't have sound too? It still doesn't have sound in here.
It's got to be the way it's sharing.
Oh no, that's
When
it.
you share the screen on Teams.
I got it. Sorry, that's the one. And let me go back one slide and come back again. And there you go. Oh, that's the same.
I think it's like the voice doesn't.
I think it's the way it's being shared.
Rig is set up.
Is it the more?
Re-entered and drilled down to
There we go.
the reservoir.
Yeah, that's it.
Just,
That's it.
just if they got it.
E2E Energy Solutions strives to design and develop economical solutions for a sustainable net zero carbon future using its patent-pending process, Enhanced Geothermal Reservoir Recovery System. E2E's EGRRS process targets qualifying producing and non-producing oil and gas reservoirs and converts them into large-scale geothermal power plants capable of generating 50 to 100 megawatts. Two to four wells are selected within 4 kilometers from each other. The wellhead is removed off of the first injection well, and the directional drilling rig is set up. The wellbore is then re-entered and drilled down to and through the reservoir, continuing to a depth that yields temperatures above 200 degrees Celsius. Once the desired depth has been reached, the drilling is then turned and continued to a central location where the recovery well will be located. The drill is then removed and the perforated pipe is installed in the horizontal zone. Once the perforated pipe is installed, the formation is hydraulically fractured. A second conduit is then installed in the wellbore and connected to the first. The portion of the conduit passing through the reservoir is designed to enhance gas liberation from the reservoir brine, which can then be recovered at the wellhead. With the gas removed from the brine, the hot fluid flows down the conduit to the fractured zone to complete the first injection well. The same process is then replicated at the second well and any additional injection wells that may be used. After all the injection wells have been completed, a recovery well is strategically located at a central location and drilled to the same depth as the injection well. Multiple horizontal legs are then drilled from the central recovery well, intersecting the fractured zones of the injection legs. The perforated horizontal recovery conduits are then installed, intersecting the injection legs fract zone. The recovery legs are then fractured, creating a deep earth radiator at temperatures of 200 degrees Celsius or higher. As the hot reservoir brine passes through the gas recovery conduit in the reservoir, the trapped gases are liberated from the reservoir brine, which then travel up the conduit to the wellhead, where they are recovered. The remaining hot brine flows down the injection conduit to the created deep earth radiator. The hot brine then slowly flows through the fractures, where the temperature is upgraded to greater than 200 degrees Celsius and is recovered by the injection legs and brought to the surface. At the surface, the hot brine is passed through a separator, where it flashes into steam. The steam is then used to drive a turbine to generate electricity. The condensed steam and water are then treated and sent to the hydrogen electrolysis process. A concentrated brine is created after the steam is separated from the reservoir brine. This concentrated brine is then treated and sent to the lithium extraction process. The recovered natural gas from each injection well can be sold directly to market or reformed efficiently into hydrogen, utilizing the produced steam and generated electricity to power the SMR plus carbon capture process. The heat recovered from the lithium and electrolysis process, combined with the electricity and clean water produced from the geothermal power plant, can be used to heat and power sustainable greenhouses. The produced green electricity can also be used to power energy-intensive AI and cryptocurrency mining. The remaining water and any carbon produced are treated and re-injected back into the reservoir, away from the production zone. E2E Energy Solutions, with its economics-first approach to renewable energy, creates green energy projects with economics that make sense.
We hope you enjoyed the video and found that it provided a good introduction to our EGRRS process. The inspiration for the enhanced geothermal reservoir recovery system came from the struggles and hurdles faced by our oil and gas sector today, and the need to start moving in a new renewable direction. As you know, some of the major problems being faced by the industry today are huge investment in infrastructure, land, and resource leases, rising costs of carbon impacting the bottom line, future demand for oil and gas dropping, the lack of economics of renewable energy projects, and bad optics in public perception around carbon-emitting fuels. E2E's enhanced geothermal reservoir recovery system was designed specifically to address the issues that are plaguing the oil and gas sector by providing a vehicle for industry to repurpose its existing sites and infrastructure, and to create renewable energy while continuing to produce their oil and gas reserves for as long as the market allows. We were able to identify that geothermal power generation from existing oil and gas reservoirs is possible in some locations, but would not be economically viable without enhancements to the reservoir. Our EGRRS process addresses this problem by enhancing the temperature and flow of the reservoir brine, which in turn greatly increases the geothermal potential of the reservoir. The second problem with repurposing existing reservoirs is the geographical location and lack of grid access, as many reservoirs are located in remote locations. We were able to overcome this problem by identifying synergies between our geothermal process and other high-value energy-intensive renewable revenue streams, which provides the potential to remove large energy loads off of the grid. The addition of these high-value commodities increase efficiencies and add valuable renewable revenue streams to raise the overall revenue and cash flow of a project. The EGRRS process also generates valuable carbon offsets and clean fuel credits, which can be used to offset carbon penalties against other carbon-intensive production or be sold directly to market, creating additional revenue, which in turn improves the overall economics of the project. I would now like to introduce Sahar Gennady, who will review the results of the simulations performed by the Enhanced Geothermal Reservoir Recovery System.
Hello, my name is Sahar Ghanati, and I am a VP of Research and Development in E2E, and I'm responsible for proving the conceptual model by simulation and modeling. Firstly, we want to start with the meaning of EGRRS. What is EGRRS? EGRRS is the concept which is hybrid of conventional and enhanced geothermal system and tries to leverage the benefit of both methods. One of the main benefits of EGRRS is that it used the previously heated water from aquifer. In EGS and closed loop, the injection is from surface that the water is around 20 degrees Celsius. But in EGRRS, the water is injected in an aquifer, and then it produced back in a fracture system. Since it is a fracture well, another advantage is that it is using the much larger contact area in comparison with closed loop. Also, since the EGRRS repurpose unused and unproductive oil and gas wells, it can help the economics by reducing the cost of redrilling and abandonment, and the pressure decline in aquifer can be maintained by reinjection of the produced fluid. I think this slide is a bit, yeah, is that the one? Yeah, here we see the schematic model of EGRRS, and as we see here, it's probably after. Okay, yeah. Let me totally mix. Okay, yeah, that slide is not the right place. The focus of this modeling is that the EGRRS proof of concept. The design and optimization of the geothermal exploitation process requires careful analysis of transient heat transfer and fluid in porous medium and hydraulic modeling of the system. And the design of the pilot and commercialization is relied on numerical modeling. To understand the relationship between water injection and heated water production and its variation in time, many components need to be coupled. And to apply the numerical modeling, we should create a structure that handles and couples all these components in one system. The target in EGRRS is to deliver 600 cubic meter per hour at 200 degrees Celsius. And to create such a rate and wellhead temperature, typical target reservoirs are numerically modeled to find the best location for pilot. The typical geological parameters and configuration is presented in this figure. And also different configurations have been modeled, and just one of them in here is presented, which is horizontal section is 2 kilometers and true vertical depth is 7 kilometers, and in aquifer temperature is 100 degrees Celsius, and average porosity is 8%, average permeability is 500 millidars. Also, the operation and implementation of EGRRS is quite simple, and current technology is available to be used. The numerical modeling is yet complex and requires many new techniques to be implemented. In this figure, we can see the complexity of EGRRS that should be considered and modeled, which are the interaction between reinjector and producer, and also the gravity flow into the hydraulic fracture zone and flow into producer. The major part of heat interaction is happening in hydraulic fracture zone. And fracture half length is one of the main parameters which shown in here. and right-hand side in a picture. As the flow moves horizontally, some of the flow moves into the fracture and then move into the producer. To calculate the actual heat transfer, the rate that goes into the well or fracture should be calculated accurately. And then different heat transfer calculation can be modeled for different sections. The heat transfer between the fracture has two components of conduction and convection inside the fracture section. That should be modeled totally different from the wellbore. That's the one. And okay, in here, the wellhead temperature versus time is compared for different half lengths, and we can see the most important component of the process is fracking, and it should be engineered properly. By increasing the half length, the temperature decline versus time is decreasing, and we can keep the temperature for longer duration. Even with 100 meters half length fracture, we can keep the preferable temperature for about 4 years. But having shorter half lengths, such as 50 meter, is not enough for power generation. For a single well, the temperature profile is compared for a well with and without fracture, hydraulic fracture. The blue lines shows the case without hydraulic fractures, and the red one shows the case with hydraulic fracture. It shows how important it is to use the hydraulic fractures and increase the heat surface. In geothermal systems, the surface facility, including the turbine, is designed for a small window. One challenge is that, what if the hydraulic fracture half length did not go as long as it's anticipated, and the temperature declines faster? Since the heating interaction with geothermal reservoirs is controlled with conduction, and the surrounding temperature took some time to recover, therefore, to extend the life of EGRRS, flow can be alternate between legs to improve lifespan. In EGRRS, we should combine the output of different wells to provide the maximum efficiency, and this design should be engineered properly. The wellhead temperature on each production well is dropping with time, and we should operate this sequence in sequence to keep the temperature in design window. As you can see in here, there are 3 different legs, and the temperature over year on a time shows in for 3 different legs. You can see how the combined temperature fluctuation is less, and with having more wells, the fluctuation can also be reduced. It must be noted that still we require new wells as we develop the project, and drilling and fracking is expected to be part of the maintenance strategy. The electrical power is one of the major outputs of EGRRS process. The enthalpy method is used for initial evaluation of the geothermal power output by the binary unit at surface. The variation of the power with rate is plotted in here. For one leg is expected to have around 10.4 megawatts. In modeling, the effect of the permeability change across the hydraulic fracture, the heat loss and gain, and that are normal to hydraulic fractures. To create the permeability variation associated to uncertainty in a hydraulic fractures, that is mostly due to geological factors and frac fluid transition. These are the challenges that modeling is faced with, and we have done work over these stuff, and these two topics is that the topics that will be published shortly by E2E, and hopefully we will be able to discuss in another events. Based on a simulation conducted, we conclude that to improve the required outlet fluid temperature, we should increase the surface area. And a minimum 100 meters half length initially would provide enough temperature around 200 degrees Celsius for a period of 4 years. Geothermal energy is not a new concept, but due to the current needs, there are different applications developing every day. The complexity of such a model cannot be captured with old applications, and there is a need for new software. We are now focused on providing a full package for geothermal from closed loop, EGS, and more complex ones such as EGRRS. The neat part of this package is that it is designed from operational concept, and also keep all the historic data in one application. Thank you. And now I would like to introduce Jim Roycroft and he's gonna talk about the financial aspect of E2E project, which is EGRRS. Go ahead.
Thanks, Sahar. Maybe I'll just get you to
Computer.
change the
Sure.
screens. Okay.
Yeah, just let me know.
Welcome. Thanks very much for allowing us to do this presentation today. I'm the CEO of E2E and have helped with the modeling the economic modeling that we've done. I guess, first of all, I just want to quickly talk about a few of the assumptions that we made when the modeling was first developed. We chose to use a model that hopefully would be able to produce all of the products that we have talked about here, electricity, lithium, hydrogen, and natural gas, and utilizing a facility size of about 50 megawatts. We don't have a reservoir at this point, so we are going on an assumption of a reservoir that we will be able to pilot in a reservoir that will prove up the economic numbers that we have developed here. So each reservoir is being evaluated for commercial use and will have unique characteristics. So having said that, hopefully we will be able to produce all of the products that we're showing here. The project assumptions, as I mentioned, we have a size of 50 megawatt. In this model, we're producing lithium, hydrogen, both green and blue, and natural gas. Water and natural gas are required or are sourced from the reservoir and sufficient to sustain operations, as was shown earlier. If there's any excess electricity or natural gas, this would be sold to market. Now, in this particular model, we have made the assumption that all of the electricity produced will be used on site. We're not, in this model, selling any of the electricity, but that certainly is a potential dependent on the site. The other thing that is not built into this model that we're still working on are carbon offsets and clean energy credits that will be generated from the production of our sites. This is we feel going to be a very big contributor to the overall economics of the project. So as I say, we are working on that now to be able to come up with what we feel would be a sufficient number generated for those credits. In this particular assumption, what we've done is we've more for, I guess, not simplicity, but to prove out the economics, we have divided the three products, lithium, blue hydrogen, and green hydrogen, a third, a third, a third. And that's what would be in our model right now. That's what would be produced. Some of the assumptions that, again, that we have estimated as far as the assumptions are, the model is concerned. First of all the numbers that you see here are in Canadian dollars. We have used an initial in capital expenditures for just a geothermal plant of 245 million. If we were to add lithium, that would be another 265 million. With blue and green hydrogen, those two would add another $85 million. So in total, for a complete plant that would produce all of those products, we would be looking in the neighborhood of $595 million Canadian. Now, going forward, are we going to need all of those plants? That would be dependent on the reservoir and what we're going to be able to generate from that reservoir. Very possibly, we may start out and just generate electricity. The commodity price assumptions we've used here are based on current or relatively current estimates, and the maximum annual production, we would be producing 2,700 tons of lithium, 15.2 million kilograms of blue hydrogen, and 2.4 million kilograms of green hydrogen. From the estimates that we have here, also we have made the assumption that in the reservoir, we would have reservoir concentration of 75 parts per million with a 90% recoverable, which would work out to 67 parts per million of lithium. We've made the assumption that in that $545 million capital expenditure, that would include probably 3 to 4 wells, and of course the surface facility to go along with that. So our production would come from 3 wells, which we have estimated would decline at approximately 10% per year. The blue and green hydrogen, the production volumes are based on the current technology of producing those 2 products. The financial results that we have has been generated from the assumptions we've made, and I'll just go to the bottom. The average operating profit is going to be around $100 million per year once the plant is up and fully running. The levelized cost of electricity, and this I think is a very important number, would be $87 per MWH, or 8 cents per kilowatt hour. in that neighborhood. And that's at a 10% discount rate over the life of the project. Now, again, this would depend, of course, on the total costs. The levelized costs would include your capital costs, your sustainable capital, as well as your operational costs over the life of the project. As I mentioned earlier, the initial capital expenditure for a complete project would be in the neighborhood of $595 million. Adding the sustainable capital over the total life of the project, we would probably be looking more around the $740 million mark. And we, in this example, have used a project life of 20 years. Okay. So the financial, just to give you a bit of a highlight here, our total operating profit based on our assumptions over the life of the project would be $2.3 billion. Pre-tax cash flow of $1.6 billion. We're estimating a payback period of 6 years with an internal rate of return of 5.4%. And we've been using a net present value of a 10% discount rate. So in conclusion, if you want to take that next.
Thank you, Sahar and Jim. The EGRRS process is a combination of many real-world technologies that are in use around the world today in a variety of sectors. For example, drilling, hydraulic fracturing, geology, and engineering. It is these synergies that allow E2E to create many new job opportunities for the energy sector by repurposing existing infrastructure and expertise from the oil and gas industry. The model shows the EGRRS process works to easily achieve its aggressive temperature and flow targets, significantly reducing the risk of the technology and positioning E2E as a global leader in geothermal reservoir enhancement and renewable energy generation. Before we conclude here, I would just like to mention, because we had some technical difficulties in the beginning, that our video is available online on our website. So for any of you who missed it or wish to view it again, please go to our website, E2EEnergysolutions.com, and you'll be able to review it there. This concludes the presentation of E2E's enhanced geothermal reservoir recovery system. We welcome any questions. And we once again like to thank Geothermal Rising and the University of Oklahoma for the opportunity to present E2E's technology and for all who took the time to be with us here today. And we'd now like to entertain any questions there may be.
Share. So. Hello.
Caesar, do you have any questions from your group there, or?
Yes, absolutely. Okay. Please hold on a second because I think that we are having some technical problems. Okay. Now, okay.
Are we all?
That was a great presentation. You know, the good thing is you went through all the entire process, including the technical, also the financial thing that is so important as well, and we sometimes miss to, you know, address that part, and you know, this is super, you know, super important. So thank you so much for that comprehensive presentation. Okay, there are tons of questions, but I'm going to start, you know, myself with one. Okay, I have a couple. The first one is, okay, in the technical part, you have one reservoir. Okay, one water reservoir that is, you know, supplying water for the model. So how you can assure, because you are producing for one interval that is, you know, closer to the surface, and you are producing, you know, through time. Okay, how you can guarantee or maintain the reservoir pressure, you know, to keep that water moving, you know, through the you know, the deeper section.
Yeah, so they're high pressure reservoirs. As we're drawing the the water out. If you remember back to the video, we bring the brine up to the surface. It's run through the process, but then it's re-injected back into the reservoir. And the reservoir is part of a bigger system that communicates with other reservoirs. So as you're displacing water, you have new brine coming in to replace it, to maintain the pressure.
Okay, so you are injecting water in both, in the top section and in the bottom section.
Yeah, we're re-injecting the brine we're producing back into the reservoir at a different location, far away from the production zone. So we're not going to be cooling the area we're producing from.
Okay,
and the
exactly.
water will work its way back to our production zone.
Okay, that's cool. Okay, and the second question is, at some part, part of the output of one of the branches is, if I recall correctly, then is 10.4 equivalent megawatts, right? That is that amount of energy is obtained with what amount of production? Okay, what amount of liters per second or barrels per day?
Speak to me.
So on that part, we producing like 600 cube an hour, and we expect the temperature at every 3 years drop to by 200 Celsius, but in that domain of 3 years, for every leg, we have the temperature above 200 Celsius. And so it's not just one time drilling. So it's a combination of coming another legs as you go. It's a very complex optimization problem. And once we resolve a lot of those concerns, me or Sar or Nick gonna give it another talk. But the way is like we're gonna shut in few legs, and we have new drilling things as we go to keep the temperature above the 200 Celsius for a small window, because the turbines doesn't like to see the temperature one day 200, another day 250, another day 150 Celsius. So we have to, the combination of the legs fluid have to be around the window that turbine provide the best efficiency. So yeah, that's a bit more complex than that.
Yeah,
I
can elaborate on it a little bit. So one leg, like you say, we could produce 10 megawatts, which is an estimate, depending on the flow we can achieve from one leg. To expand on that and to expand on the longevity of our resource from a 4 to 5 years to 20 years, we're going to be utilizing multiple legs. So we'll have multiple injection legs tying in to the recovery leg. So to achieve the flow that we're going to require for higher production, and also to increase the longevity of the reservoir.
Okay, so you are, drilling one leg, let it produce it, then once make the other leg, and
actually,
you're handling the temperature, because you want to maintain those 200 Celsius degrees kind of constant, if possible.
Yeah, but a facility will have more than one leg, depending on the production or the generation that we're targeting. So if we're only targeting 10 megawatts, it would have one leg. But if we're targeting a facility that's 40, 50 megawatts, it's going to have multiple legs to achieve that flow. And also the additional legs, by adding additional legs, you're slowing the flow per leg, which also slows the cooling process and increases the longevity of the radiators.
Okay, yeah, that makes sense. Thank you. Okay, guys, do you have any questions? Yes, okay, please come.
Thank you so much for the great presentation. Yeah, I have some questions. I hope they're not funny. Okay, so the first one I just wanted to confirm. Maybe I saw it right. Okay, so you said so the EGRRS you try to convert non-producing wells to geothermal wells by going deeper.
We do. Great question. That's our primary focus.
Okay,
so we do target non-producing wells with high brine contract, good communication and permeability, and we do just that. So we re-enter the well and we take it deeper. So we're going to drill into our reservoir, through the reservoir to the depth that's going to yield the temperature we desire, and that's how we upgrade it.
Okay, so
by running it through the fracturing zone.
Okay, thank you. So it's going to building on that. So most times when you go deeper, you do you drill to volcanics, or you still maintaining some sedimentary when you drill deeper?
We'll be drilling down probably to the granite formation. It's going to depend on the gradient in the area on how deep we have to go to achieve our desired temperature. We target above 200 degrees Celsius. So if we got a very strong gradient, we may only be down 4 kilometers. If it's a weaker gradient, 35, it may be up to 7 kilometers in depth.
Okay, yes. Okay, so yes, and building on that again, I'm getting closer to the destination of my question. They're trying to maybe map what you should expect at such depths. Probably, is it only seismic you use to image the volcanics that you target? Is it only seismic, or you use tellurics or other methods?
No, we use temperature gradient, and we look for adequate permeability in a reservoir, so we can have adequate brine. The temperature gradient tells us the depth we're going to, and we're going to be into hot, dry rock, so granite. Is that maybe I'm misunderstanding your question?
Oh yeah, but the reason I asked this because I was like trying to ask the deeper formation that you're going to, like definitely the volcanics and the granite. So what geophysical method do you use to image that formation that you're trying to?
It's seismic imaging.
Yeah. Oh, okay. So I was asking because sometimes, not all the time, the seismic around for the volcanics might be quite not really clear. So I was trying to ask if you kind of amplify that seismic with some other geophysical method, or you only depend on the seismic.
Yeah, let me explain that part. Because we trust that part mostly on. So it's operators. We've been operating the field for a good amount of time, so they have good seismic data. They have lots of vertical wells that they kind of calibrate the temperature with those seismic. So, and that part, in the future, we may go and dive in and do more research type of thing and try to find out the best thing. But the GRC and the Albertan, like a geology survey, and a lot of those people are working on that. And these fields are not like we just got them yesterday. They've been operating for like 5-6 years, and so validation of the temperature wells and those stuff with the seismic. And if it's not accurate enough, and we drill it, and we may go longer. So we always have that capability. So we're gonna do and calculate the temperature as we go to drill it. So it's not just we go there and say, oh man, like it's not 250, what we do now. So we have a plan to go, but we are probably in the ballpark plus minus 10 Celsius and can tell which depth we should go. So we are pretty sure about that thing. The gradient of the reservoirs and the fields, like from 2 kilometers to 3 kilometers and 4 kilometers, once we got those numbers, it doesn't change rapidly once it goes to 5 kilometers. So it's a conduction system. The magma, once you are in magma, everything's from that point on is mostly conduction. And that's the best physics in the world that you can calibrate and validate. And we're not going that deep and touch magma. We are way above that one. So, like we are in the conduction zone of a reservoir. If I answer you properly, I'm not sure.
Yeah, definitely. And sorry.
One more.
Okay. So the last question is that in all the experiences, I'm asking lots of questions because I don't understand most things about. So that's why I'm asking lots of questions. So in your experience of this operation, have you maybe experienced some situations where the formation you drill into, you have some maybe unmapped fractures that create some kind of migration paths for fluid leakage from the targeted reservoir? Have you ever experienced something like that?
Let me elaborate that one, because the method we have, the EGRRS, is a combination of EGS and a combination of closed loop. We are some sort of the middle of those, and so we have the estimate of the people have done in the granite. So, for example, in the Everloop for the conduction, the loss are, it's about 0.7 cube a day. Like that's pretty tiny. And in the EGS, they don't know because they're trying to create the fracture, and none of those EGS at the moment at the level that you know about how much you inject, how much you got back, like it's on the, but at least we got a few points that we know. If you're not in the super fractured granite, that what we're wishing that we will be, that we can fracture. If it's a super leaky granite, then we got an issue on fracturing it. So we can't even create the harder fracture. So we hope for something that's not crazy leaky, and we got an estimate of the leakiness once we do the harder fracture. But they tell you estimates on at least ever done the closed loop is open conduit. The loss is pretty tiny, and that's going to be better in our case because we go pretty deeper. And as you go deeper, the permeability drops, the rocks are more confident. So if that's the question.
Definitely. Thank you so much. Thank you so much. Okay, we have another question. So, okay. Carelia. Okay.
Hi, how are you? Thank you so much for your presentation. I do have just 2 questions, okay? Very quick. So, so the first one will be, I know that your plan is to drill in deep zones. However, how do you mitigate induced seismicity? And do you consider this in your simulations?
Yeah, you know, that's a complex one. A lot of funding, especially in DOE and US, and the biggest concern is the geothermal is the rank 2nd, looks like, on the harder fracture, 4th on the harder fracture. So yeah, we're not in that stage. We're trying to, at the moment, make the pilot works and the system works. And then once everything works, then we have to do extra simulation. At the moment, we can capture everything about like harder fracture, geomechanics, and those ones. But we don't have the capability of simulate the fractures open, closed, and causing seismicity as a result of. We may go that direction if that's a concern by the Albertan and BC, British Columbia, and Canada government. That's possible. It's not hard to do. But the problem with the simulation, whatever you do, at the end, you are wrong. So, but you want to be directionally right. So we hopefully, once we got everything set up and validate with the pilot, everything, then we are in the good mood and good stage that we can go and investigate those stuff.
Okay, thank you for addressing that question. And the second question will be, what would be the optimal well diameter for injector and producer? The diameter of the well.
So we do like 6-7 inches, like we varied all those. And the conduit, the bigger is better. But the problem with this method, it's not a problem, but that's one of the things we're going to drill everything telescopic. All right. So we drill something, we have to go smaller, and then we go the production zone to the aquifer is smaller. We can't just go smaller and then make it big. So we are one direction. It's a telescopic way. Like we have to go and make things smaller. And hopefully, and the point is not to change the main vertical well that is going to be abandoned. So that's the only restriction for us. But yeah, anything above 6-7 inches would be awesome for this. Injector, there's no issue because injector doesn't cause any issue. The tubing that we put in injector, that's a problem. Like the casing and those things are way big. We're not gonna, yeah. So that's not. It's all the concern about injectivity is the deliverability of the reservoir. And Nick and Vince actually work on about all the aquifers inside the BC and they find the good ones that we can go. It's not something that we can just say you're in the middle of Paris and you want to do this and we say yes. It's some sites that makes these things possible. It's not just everywhere in the world that we can run this.
Okay, thank you. And probably the very last question will be, as we drill deeper, our uncertainties also increase. So we are talking about actually counts of uncertainty and not ellipses or something else, okay? So uncertainty increases. So you take that in account in your simulations as well to keep like a proper distance between wells and also the fractures. So one fracture system is not affecting so much the other and hitting hard the well and things like that.
So that's what SAR actually covered, and the whole point of simulation was what's the important factors are. So that's SAR, and based on the simulation that we done at the moment, the SAR done, is hydrofracture half length is the most important thing, and we did sensitivity on that part, but how big gonna be the hydrofracture that's a different story, because the problem with that part is there are few points in the world that we can create and validate the models that we are using on the shale oil. So hydrofracture models are all created based on the shale, the toughness you put, the elastic modulus you put, like no one's done in the granite. So, so that's one big uncertainty for us. That's what the SAR did, like all sort of a different thing, like assuming like, what is this half length changing, descending, ascending, like this go, like how big aperture would be affecting. So, but among all, the biggest concern is half length. And that's really important, because if you can't create the fractures long enough in these reservoirs, then that's going to be an issue. And that's something mitigate the EGS at the moment. We don't have the concerns that the EGS has on the sim breakthrough and those things, because those doesn't hurt the process. But we still have the challenge. What if you can't create the half length of 50 meter, 100 meter that we want? So, yeah.
Well, I really appreciate you taking the time to provide this talk, and have a good day. Thank you.
Thank you.
Thank you.
Okay. Okay. Now next question is coming. So, okay.
Hello, I have a really quick question. Like I saw on the slides and on the video that you have like the injector well is on top of the production well always. And I wondered if that it was used for the presentation or that is always the case, and why is it that way?
Yeah, the slide, it's the injector well. And are you talking about the re-injection well? I'm assuming that's what you're talking about. The re-injection well is actually located a significant distance from the injector to avoid any cooling. So that's going to be once you've run your brine through the system and it's cooled, it gets re-injected at a further location. I understand what you're saying. It kind of appears in the image that way, but it's not actually like that in the real world. It's further away, significant distance away.
At least kilometers away.
Okay, but is it always like the injector is on top of the other, like in a less deeper than the other?
Okay, maybe we're getting them confused. The injector, where are you talking about the injection into the system? So where you're first
like on the video and also on the slide, like you see the injection pipe, and then this is the production in here.
Yeah, and it's simplified for the video. In the real world, you're going to do your injection legs and your recovery legs the most economical way, and that are going to yield you the best results. So it may be like drilling down into the reservoir and a sweeping motion towards a central location, because you're going to have a number of wells making up your injection wells. So you want to try to get somewhere central where you can place your recovery well. And so your injectors will go, and your recovery well is going to inject those fractured areas. So it'll have a number of legs off of the recovery intersecting the injection wells that'll be coming from different locations depending on where the initial wells were located.
Okay.
That answer your question?
Yep.
Okay, perfect.
Okay. Any other question? Yes. Okay. Okay. One more question.
Hi. Thank you for your presentation. My question is a little more academic. So the idea is just to create more surface area, improve permeability to extract heat, right? In the oil and gas, they use propane. In EGS, we don't use propane, mostly for stability. Have you guys, how do we keep those fracture open? Like you just assume just slip shear and then the fracture just auto self-prop themselves, or?
Yeah, so Either or.
Okay.
Let me explain that part. The reason that you see in the EGS that not using it because it's an earlier stage, and they're not dealing with the plastic rocks like a shale oil, like like a plastic rocks. The assumption is once you break the granite, like you have it like on your kitchen, like a granite. Once you break it, your kids, if you have kids in a room and you break it, they don't get back, and that's not the case in the shale oil. So that was the thing, and that was one of the things. Like so, once we have a site, we have to think about what's we're going to go, and the best driver of using the proppant and not using proppant, or like what we're going to do is the brittleness index. That's we're not going to create the wheels again. So we're going to go the same approach that everyone does, and I think with this process we're going. Probably we're not going to use proppant because if we even use proppant, after a few days or a few months, we're going to produce all of it because the condition of the granite is so different than shale, and that's why they're using proppant in that case because things are closing and you keep the proppant there. But we're going to evaluate that more. We're just trying to do the CFD simulation on that part, adding it to the module and see how that thing's going to work. Because all the softwares not have the proper transport modeling properly, and that's what a lot of academics, and your PhD is on that, probably that's what you're asking. The CFD is the best way to go, and because there's no commercial package, and we create our own software in this case, so we add in the CFD module to see what we're going to be. But it seems like what you do all these exercise and do things. You have to wish us the best of luck because this is the first time we're doing this thing. So, but we think we're not going to do proppant with these rocks we have.
Thank you. That's what PhDs are for, right?
Yeah.
We'll investigate that for you guys. All right. Thank you.
Thank you.
Okay, thank you so much. Okay, any other question here or any other question from the people that is connected?
There was one question, but it was answered because one of your somebody already asked it. So
yeah, that's true. Yeah.
Yeah. So I think I sent out a text seeing if there's anything else, and at this point, there's nothing else on there.
Oh, okay. Let me. Oh, yeah.
And Caesar, that was a short notice for us, so we couldn't prepare something like more technical for you guys. So that's in the future we're gonna do one more. It was like 2 days. It was we have a lot of document, but put in the meaningful presentation that takes a bit more time. So.
Actually, we are super glad with this style of presentation because this is a thing that we need to address. No, those projects are driven by economics, and numbers and financial numbers are important. If financially a project don't close, okay, you have no project. So yeah, addressing holistically as you show was super good. Okay, this is also enriching this conversation, and probably hopefully we can have in the future a presentation that address basically economics. Okay, this is a good thing that we have thinking in the future, because this is so important. No, in that case, don't hesitate. Don't. Actually, this is a super good interaction. I see, the amount of people that is connected. So, the topic was attractive. Thank you so much for bringing that this topic with us. Also, that is very innovative, and this is a great concept. You are addressing not only heat, also lithium, hydrogen. There are you are extracting. There are a lot of elements that makes this concept very attractive, very appealing. So, okay, thank you so much for bringing that information with us, for sharing that with us, and we are super happy, guys. Thank you so much. And,
excellent.
Thank you.
Thank you. Have a great day, everybody.
Yeah, you too. So, okay, next week we have another speaker. So keep connected with us. So thank you so much. Have a great, a nice rest of the week. Thank you.
Bye-bye.
Thank you.
Thanks.
Bye-bye.
Well, that was a good group.
Yeah.
How many people show up? I don't have my glasses on. How many people show up? Farza is there too.
There I think there was about maybe 10 or 15 or 15